Okay, so yesterday we talked about Hooke's law, and then we went over how Hooke's law relates to forces and springs, and then we went forward on that to how it relates to elastic potential energy in a spring, okay, and then for an oscillating mass on a spring system. Okay, so that's the stuff we covered yesterday. We're going to continue working on that today. We're going to do a couple of things with that. The first thing we're going to do is kind of a little demo activity here on Hooke's law. Okay, so what I've got up here is a Hooke's law apparatus. Basically, it's a hanger and a spring. Okay, because that's all Hooke had when he discovered his law, was a spring hanging from a ceiling. Okay, what we're going to do is we're going to put different amounts of weight, in other words, force, on this spring and measure its length and then see what we can get from that depth. Okay, and that's basically all we'll be looking at in terms of Hooke's law. Okay, then we'll go into a few more examples of Hooke's law and conservation of energy and simple harmonic motion. Okay, and then tomorrow we'll be moving on to a pendulum lab. Okay, that we'll be doing in class. Okay, so what we're going to start out with is this spring with no weight on it. Okay, so what's its displacement right now from equilibrium with no weight on it? 0. All right, as I add weight, it's going to get longer. Okay, and we're just going to measure how much longer it is than its unstrained length.
Would it be stretched out a little bit by its weight?
That's what we call it. It's unstrained length. There's no weight other than itself on there right now. Yeah? Okay. So right now then, the force acting on it is 0. So we're just going to kind of fill this chart in here. Okay. Actually, I'm going to fill it in Google Sheets where I have it here. All right. So right now, I've already got that when the force on it is 0, the displacement is 0. Okay. There's no displacement from equilibrium with no mass on it or no force on it. Okay. So what I'm going to do is I'm going to put the first weight on there right now, and that's going to be 50 grams, which is how many kilograms? 0.05 kilograms. Okay, so how much weight am I putting on it? Right. Okay, I'm going to take the mass that I'm putting on there, okay, 0.05, and multiplying it by 9.81, which should be 0.004905, I think. 0.4905, I put too many zeros in front of that, 0. Okay, so 0.4905 is going to be my first force that's going to go on there, okay, and we'll see how far it stretches the spring. Okay, so the new length of the spring, once it stops moving, is going to be 0.024 meters. So I want you guys to kind of draw this chart here that I'm drawing in here. Okay. So that we can kind of see what this is going to look like. The force I just put on there was 0.4905 newtons. Okay. Next thing I'm going to put on. So I'm going to take that hook off. Okay, and I'm going to add a little bit more mass. I'm going to add another 10 grams. Okay, so now I've got how much on here? 0.06. Okay, I've got 0.06 kilograms on here. Okay, and if we do our force calculation here, so we're going to go 0.06 times 9.81. All right, now we're looking at 0.5886 newtons. And the new length of the spring is 0.033 meters. Okay, now, when I keep adding mass, this thing should keep getting longer in what kind of a fashion? Yeah, it should be linear. Okay, hope so anyway. Okay, I'm going to add another 10 grams. I'm going to take the 10 gram one off and just put a 20 on here. Okay, so now our length is 0.039, okay, and our force on there is going to be 0.6867 newtons. Okay, is this looking like it's fairly linear? Fairly, right? So far, anyway. Okay, I'm going to put another 10 grams on there. Okay, so we got 0.045 meters on there now as the length, and we had 0.7848 for our force. All right, so we got one of these that's out a little bit, but the other ones are looking pretty consistent or pretty linear here. And, you can actually remeasure that first one in case I measured it wrong. And I did. In fact, I measured it so wrong that it's exactly what it should be when I measure it right. So fix this one, guys. Okay, so what are we noticing here? Now that I fixed that one because I read it wrong. It's an absolutely linear increase. Okay, it's by 0.06 each and every time. Okay, all right. So we'll put just throw on here. All right, this will be our last one, so I'm going to put 0.09 on here. Okay, so we got 0.8829 newtons on there. And it's exactly what it should be, which is 0.051 meters in length. Okay, so now I'm going to build a quick graph out of this, and I'm going to ask you to calculate something from it for me, actually a couple of things. Okay, so we've got our equation on here. Right, we've got force on the y, we've got displacement on the x. I want you to calculate a couple of things for me. Okay? And all right. I want you to calculate the spring constant, or figure out what the spring constant is, okay? And then I want you to calculate the force force required for a length of 12 centimeters. Okay, and a length for the force of 1.5 newtons. Okay? I want you guys to figure those things out, given what you have here. Yeah, spring constant for this is 17.3 newtons per meter. Okay, it's 17.3 newtons per meter. How do I know that? Okay, that's what the equation says, but how do I know the slope of this graph represents the spring constant? Okay, first off, the units come out to newtons over meters, okay, which is what the units for spring constant are, okay, but also, because when I calculate the slope, I'm dividing force in the spring by x, right? Isn't that how I calculate according to Hooke's law? How I calculate the force in the spring? Okay, those are the kind of things we need to be able to notice, okay, kind of by looking at a graph. All right, if I want to calculate the force required for a length of 12 centimeters, all I have to do is use the equation. All right, so for that one then, we're going to be looking at, so we're looking for the force, so we're looking at solving for y. So we'll have 17.3 okay, times 0.12 meters plus 0.00904. Okay, so we're looking at a length, or sorry, force of 2.1 newtons. Okay, and for the length for the force of 1.5 newtons, okay, we're going to have y minus b over x, so that'll be 1.5 minus 0.00904, okay, divided by m, which was 17.3. All right, so we'll be looking at a length of 8.6 centimeters. Everybody all right with that? All right. I would like you guys working on some of these questions from the workbook on conservation of energy and in mass on the spring and stuff. So I'm going to pull those up and put them on the board here. Okay, and if there's any ones we need help with, then I'll go over those. Okay. So for question number 5 here, guys. So on this one here, we've got, this is a Hooke's law question. Okay, we have a mass of 5 kilograms, which means that its weight, okay, is going to be 49.05 newtons. That weight is pulling down on the spring. So when I hang it on the spring is pulling upwards with 49.05 newtons worth of force. Okay, it's stretching it 0.0325 meters. It's in centimeters, so I got to convert it to meters. Okay, so if I'm looking for K, force in the spring is negative K times X. So force in the spring divided by negative X, or even just X, because I'm looking for something that's an absolute value anyway, it is going to be 49.05 divided by 0.0325. That should give me 1,500 newtons per meter. So, yeah. Any other ones giving us trouble? I take requests. Okay, we'll be working on it then.